Welcome back. This is the 15th lesson of algorithmic design, and during this lesson we will talk about the deletion from, we will conclude as topic the deletion from regular trees, and we will do some exercise about recursive equations. So first of all, let me recap what we saw until now about regular tree. During the last lesson we saw that regular tree basically are an enhancement of binary search tree meant to reduce the maximum height of BST themselves. So this is done by imposing some conditions, and in particular we introduce the color of the nodes. Each node in a regular tree can be either red or black, and any red color can only have black children, while any black colored node may have both black or red children. So it's not really relevant once you are dealing with a black node. Moreover, another important condition, there are many conditions, and we saw them on the slides. Another important condition is that once you have chosen a node in a regular tree, all the path from that node to any descendant leaves in the regular tree itself must have the very same number of black nodes. And by using this definition, we define the black height and because of this definition we define the black height of a node, and we prove that in any regular tree the height of the tree itself is logarithmic with respect of the internal nodes of the regular tree. So as far as the insertion concerns, we saw that the insertion begins with the insertion such as we did in the BST, and in order to preserve the condition for which every branch from a specific node must maintain the very same black height, so the very same number of black nodes, we decided to color by red the new node due to the insertion. This of course may end up in a situation in which you have two red colored nodes in row, and if this is the case, we saw how to solve to fix this situation. This is basically due by applying three different rules, which are connected to three cases, which are related again to the uncle of the node we are dealing with. So we have a node, its parent is red. For sure, since its parent is red and we are dealing with a regular tree, the grandparent of the node we are dealing with must be black. And so to decide whether we are in condition 1, 2, or 3, we simply have to look to the uncle of the node we are dealing with. So if the uncle is red, we are in condition 1. If the uncle is black and on the same side of the node we are dealing with, we are in condition 2. Otherwise, we are in condition 3. And we saw that the worst case scenario is when we keep applying condition 1, which basically solve the problem locally and may push it towards the root. Okay. And so the complexity of the insertion, of fixing a possible problem due to the insertion on the regular tree is basically logarithmic with respect to the number of internal nodes of the regular tree itself. We were discussing about the removal of a key, and again we reduced the removal of a key in a regular tree to the removal of a key in a binary search tree, which as you may remember is basically reduced again to removing a node which has at most one child, okay? And again, due to the rule for which we want to preserve the black height of any branch in the tree, if the node to be removed is red, well, nothing change. We are not breaking any rules, regulatory rules in our tree. Otherwise, again, so if the node we want to remove is black, we need to perform some fixing, let's say, and why we must perform some fixing? Because in the branch moving from the parent of along the parent of the node we want to remove and the child of the node we want to remove, the two, so the parent and the child must be both red, and so we need to fix this situation. Moreover, we decreased by one the number of nodes. Moreover, for sure, we decreased by one the number of black nodes on that branch. So, in some sense, the child of the node we removed, which is now in the position in which was the node we removed, as a kind of debit, black debit with respect to the overall tree. So to fix this problem, we saw that there are many cases. Either, let me go to the slides so we can recall all of them. And in this case, the cases are basically related to so this is case 0. So of course, if you are dealing with a node, so if the node which was the child of the node we removed is red, you simply have to color it black. Otherwise to choose in which case we need to have a look to the siblings of the node we are dealing with. And for instance, in this case, so this is case number 1. The node we are dealing with is X, and his siblings, which is W, is red. Well, of course, we may simply, in this case, we may simply have, as we saw, we may simply have a recoloring of B and D, and then left rotation, and this hasn't solved the problem. For sure, meaning that again, yeah, we may have a problem on this node, which is basically exactly the same we were dealing before, but in some sense we change the situation with respect to the original one, and we will see why in a while. Another possible case is this one. As you see here, by applying rules number 1, we end up in a situation in which the siblings of the node we are dealing with is now black, which is different, of course, from case 1. So this may be case 2, in which we have we are dealing with a black node, its siblings and its nephews are all blacks, and this situation can be, so this case can be dealt by recoloring basically W by red. In this way we are decreasing the number of black nodes of the branches moving along W, and we are decreasing by 1. So right now, so by recoloring W by red, the branches moving along X and the branches moving along W have basically exactly the same number of black nodes. Okay, so if you remember that X as a kind of debit, black debit, so if we reduce by 1 all the branches moving along W, we end up in a situation in which all the branches moving along X and all the branches moving along W have exactly the same number of black nodes. So, right now we fixed, by recoloring W, we fixed the problem on these two subtrees, of course, and on the subtrees rooted on this node. But it might be the case we disrupt the rule above this node, and so we have to keep applying all these rules from this new node. Okay. So the new node we need to deal with is this one, okay? And this is case 2. Now we were dealing with case 3 at the end of the last lesson, and case 3 is quite similar to the previous one. I mean, the previous one, the siblings of the node we were dealing with and all the nephews are black, while in this case so the siblings is black, the sibling of the node we are dealing with is black, a nephew, well, the nephew on the same side of X is red, okay, while the other nephew is black. So, and this is the case. What if we are in this case? Well, if we are in this case, we can simply change our situation by recoloring C and D and apply a rotation. As we saw the last time, in this case we are not solving situation, because again the number of black nodes below this W, so the siblings of X was one more the number of black nodes below X, and so it is after the transformation. So if I'm wondering what's the number of black nodes below C, well, the number of black nodes below C is the number of black nodes below this node, which hasn't changed, plus 1. Okay? And which is exactly as they were just before the transformation. So we haven't solved the problem again here, but we change the rules in some sense, because right now we are moving from a situation in which the siblings on the opposite side, well, the nephew on the opposite sides of the node we are dealing with was black, to a situation in which the nephew, which is on the opposite side of the node we are dealing with, so this is a left child, while this nephew is a right child, now is red. Okay, and why this is interesting? Of course, this is interesting because of the fourth case, which is exactly the situation I just mentioned. So in this case we are dealing with a node, which is the node X, whose siblings is black, and whose nephew on the opposite side, so this node, is red. So we are not interested in what's going on the other nephew. We are not interested in what's going on the black on the parent of the node we are dealing with. By the way, can you send me an acknowledgement just on the chat, just to know that you are there, please? and I was saying, okay, so this situation is quite similar to the previous one, but we are not interested in what's occur on the to the nephew. So what's the color of the nephew, which is on the same side of X, and we are not interested on the color of the parent of X, I was saying. Okay, so so if we compare case 2 and case 3 and case 4, they are really similar. Really similar. As you can see here, we have a nephew, red nephew, and we have a red nephew, but they are in different position. Okay, so while in case 3 the nephew is on the same side of X, in case 4 is on the other side. So if we are in this case, oh, by the way, notice that this case also covers the situation in which all the nephews are red. Okay, so for sure this is the last case, because we have considered a case in which X is red, which is case 0. We have considered a case in which W is red, which is case 1. We have considered, well, no, in the case 1 is this one. We have considered the case in which this is it, and let me see. Okay, this is case 1, so we have considered the case in which the siblings is red. We have considered the case in which all the siblings, all the nephew are black, which is case 2. Case 3 was this one, and this is case 4. So these are all the cases of the removal, to fix the removal of a node. So what can we do once we have decided, we have established that we are in this case? Well, we can simply switch the color between X parent and siblings. So basically, if this is red with red color D and with black color B, if this is black, we simply left all the nodes as they are, and then we need to black color this node. Okay, and once this is done, we simply have to apply a rotation on the left side for this example, of course. So let's try to figure out what's going on here. Case 4 means that C can be red, right? Yes, as I said. So one of your colleague is asking, can C be red? Yes, it can. So as I was saying, here we are considering both the cases in which C is black and C is red. Okay, so let's have a look at this situation. At the beginning of case 4, we were dealing with a node which has a black debit, let's say, with respect to its sibling. So the number of black nodes belong X is the number of black nodes belong W minus 1. Okay, so now let's have a look to what's going on here. So right now A is at the same level of C. So the number of black nodes belong C is the number of belong C is of course the number of black nodes belong C is of course as the number of black nodes belong A, because C is under D. Okay, so these two nodes have the same number of black nodes belong them. Okay, what about B? Well, if I count the number of black nodes belong B, now the number of black nodes belong A plus 1. Okay, and what about E? Well, E, which was red, has a number of black nodes belong in, just like W here, minus 1. So now E is black, so the number of black nodes belong B is equal to the number of black nodes belong E. Okay? So by applying this rotation, by applying this recoloring, we end up in a situation in which the number of black nodes in belong B and E are exactly the same. The number of black nodes belong A and C are exactly the same. Now let's try to compare the number of black nodes belong D and belong B just before the rotation. Okay, so I haven't changed anything below this node. So the black node belong A is exactly as the black node belong A just after the rotation, right? And as you may remember, this node was in debit, so it's missing one black node with respect to its siblings. So the number of black node belong B is of course the number of black node belong D plus 1. Was at the beginning of case 4, of course. Okay, so let's now have a look at this case, so just after the rotation. So just after the rotation, the number of black nodes of D, just below D, is the number of black nodes just below B. Why? Because the number of black nodes below A is equal to the number of black nodes below D minus 1. So since I'm looking to the new parent of A, these nodes must have as much, so in any branch moving from B to one of its descendant leaves, the number of black nodes should be of this below B must be equivalent to the number of black nodes below D. So by below I mean below on the path moving from the node itself and its descendant leaves, of course. Okay, so no, I'm not talking about the number of black nodes on the whole subtree. I'm talking about the number of the nodes on the branches. So right now I'm in a situation in which B must have the same number of nodes of W, and of course, as we already proved, also E has the number of nodes of B. So this node, so the node D just after the case 4, has as many number of black nodes below him as add B on the branches moving along W. Okay, so by applying case 4, not only I've solved the situation on the subtree D, but I haven't changed the black node 8 of the root of the subtree. Well, of course I changed the root of the subtrees, but from the point of view of the node above this node, nothing has changed. Okay, so the number of nodes below, on the branches below B, moving along W, along D, are exactly the same number of black nodes from D to its descending leaves. So case 4 basically solved the situation. So solve the problem. No more debit. Everything has been fixed right now. It has been fixed on the sub 3 rooted on D and above. Okay. So case 4 basically, as one of your colleagues observed, restore the red by 3 property. Okay. Why? Again, because by applying case 4, not only we have fixed everything on the sub 3 rooted in D, but the number of black nodes on the branches moving along D to its leaf descendant leaves have the same black 8 of the branching from B, on the branches from B to from B and D to their descendant leaves. So we don't need to fix anymore anything. The color of B is the color of D, so anything has changed above. Okay. Let me read one question. I changed the color and then I rotate the tree so I rebalance the branches of X parent, like a leveling. Not. I don't know what you mean by leveling, but for sure, I'm not guaranteed to rebalance the branches of X parent. For sure, I rebalance from the black point of view the branches of the parent. So it could be the case that one of the branches of the parent is much larger than another due to red nodes, but from the black point of view, so from the point of view of the black nodes, they are just after the rotation, they are exactly the same. Okay, so the point is that this node is at the beginning was missing a black. Well, all the branches moving along this node was missing one black node because we remove it. Okay, so we need, in some sense, to increase the 8 of all the branches, the black 8 of all the branches moving along it from above, for instance. So yeah, so we need to place this node at this level. Why? Because all the branches moving along C, for instance, have one less node with respect to X, because already moved along D. Okay, so as you can see here, by applying rotation, we solve the situation. And why couldn't use the very same strategy in the previous case? So in case number 3, well, the point is that by applying a left rotation, we end up with with this nephew, which was which is the nephew of the node we were dealing with on the opposite side. This was black, and so we couldn't recolor it by black, and so it turns out that by applying this very same strategies to case 4, we end up in a situation in which basically we had moved the problem from this node to this node, and that's why we need another case. Okay. I add a new black node in the tree, turn the causes into black node, and then shift the node, rebalance black tree, remove black node, and before also add a new node. No. Well, you add a black node by coloring this node, so E. So you basically you are basically recoloring this node to a black node. And so you are increasing the number of black nodes on the subtrees, basically, okay, rooted in B, but you are not adding really a new node. However, I mean, the point here is that, let me repeat it for the very last time, and then I would like that you try to figure out what's going on by your own during the Easter vacation, the Easter holidays. And so let me repeat once more what's going on here. Here we are basically in a situation in which this node is lacking of, as a debit, is lacking of one black node below him, with respect to its siblings, of course. Okay, because we removed one node. So you have to figure out the situation in which, in this position, there was a different node, black node, and that node was removed due to the fact we want to remove a value from the red black tree. So to remove it, we simply delete the node and replace it by using its only child, which is this one. Okay. So since the removed node was black, right now this node has a number of black nodes below him, of course, in each of the branches, smaller with respect to the number of the node below this node on each of its branches by 1. Okay, because this node was at this level just before the removal. Okay, so to fix the problem on this branch, we need to figure out something. And in this particular situation, we can solve the problem simply by swapping the coloring of these two nodes. Okay, so if this is red, just after the transformation, D will be red. If this is black, well, everything stays still. Okay, and then applying a left rotation. Okay, so let me leave the recoloring of E stand still for a while, and let's focus on this subtree. So the subtree, new subtree rooted on D. So after the rotation, the number of nodes below A should be equivalent to the number, must be, well, are for sure, equivalent to the number of nodes below C. And why? Because as I said, just before the application of case 4, we were saying that this node should be at this level, if you remember. Okay, because as one black node less than this one, well, one black node less than this one. Okay, on the branches moving along him. So just after the transformation, we end up in a situation in which A is placed exactly at the same level of C. So they are fixed right now, and we are in a situation in which B, which is now black, has one more node with respect to this one below him. So B has one more node with respect to A, one more black node below him with respect to A. of course, because below A we have alpha and beta, and below B we have A and alpha and beta, okay? So let's try to see how many black nodes are below E. Well, E was at this level. So just before the transformation has exactly as many black nodes as C below him. Okay? So if I have a look to this node, I end up in discovering that if I need to recolor it, otherwise the number of black node on the branches moving along it are missing one node with respect to B. So this is a kind of specular situation with respect to case 0. If you remember, in case 0, let me go back to case 0. In case 0, this is case 0, we were dealing with a black node, with a red node, and we need to fix the situation. To fix the situation, we simply have to recolor it by black. And this is enough. Now, in the second part, let's say, of case 4, we have recolor B and D. We have applied the left rotation, but the black coloring of V stands still, let's say. Okay, so let's figure out a situation in which we haven't red colored it. So now, because we haven't black color it, because we haven't black color it, we are dealing with a node which is lacking of a black node below him, and so we are in the specular situation with respect to case 0. So how can we solve it? Well, again, we can solve it simply by recoloring, black coloring E, and this is enough to solve the problem. Okay? So, just to recap, case 0. Case 0 solve the problem in constant time, because we have simply to recolor the node we are dealing with, and we end up in the situation in which everything is fine. Case 1. In case 1, we are moving, we are applying a rotation, we are recoloring two nodes, and we are moving our problem towards the leaves. We are moving our problem toward the leaves. Okay. Well, we are pushing actually the node with the problem toward the leaves. Okay. And what about case 2? Well, in case 2, we are increasing by 1. We are solving the problem on the subtree rooted on B, so on the parent of the node we are dealing with. And just after the transformation, the new node we must take care of is the parent of the node we were dealing with at the beginning of the transformation. So we are pushing the problem. We may be pushing the problem towards the root. Okay, in case 3, basically we are changing the structure of the red-black tree from this situation to this situation, which is directly applied to case 4, which is this one, and by using case 4 we are able to solve the problem in constant time. Okay, so all the transformation takes time constant, takes constant time, so theta 1. Both case 1, case 0 and case 4 fixed the red-black tree in constant time. Case 1 cannot occur twice in a row. Let me go back to case 1 just to show you why. So case 1 was this one, so we were dealing with a black node whose siblings is red, and by apply case 1, of course, we end up in a situation in which the siblings is no more red, is black. Okay. And what about case 2? Well, case 2 push the problem one step toward the root. Okay, and we observed it just a while ago. So if case 2 occurs just after case 1, the next case should be case 0. Let me go back to show you the situation. So this is case 1. We basically have a black node. After the case 1 we were dealing with we are dealing with a black node whose parent is siblings and whose siblings is black and whose parent is red. Then after case 1 we apply case 2, and this is done simply because this is easy to see, because just after we are dealing with a black node whose siblings is black and whose parents are whose nephew are black. So if we apply case 2 just after case 1, we end up in dealing with the parent of the node we were dealing just before case 2. So if we take case 2 just after case 1, we end up with dealing with the parent of the node we were dealing at the beginning. And since case 1 plays in a situation which the parent of the node we are dealing is red, just after applying case 2, the new node in which considering should be red. Okay, so if case 2 occurs just after case 1, we can apply case 0, and then we can fix the regular tree. Okay, as we already observed, just after case 3 we can apply case 4. So the only chance to keep repeating all the operation for as many times as it is possible is to apply case 2, let's say, until we end up in the root. Okay, so let me repeat this point. We saw that case 0 and case 4 fix the problem, and they can be handled in time θ1. It's easy to see that case 1 cannot occur twice, because case 1 is dealing with a node in which his siblings is red, and planes in a situation in which both the node we are dealing with and its siblings are black. Case 2, which is the case in which the node is black, the siblings and his nephew are black, basically push the problem one step toward the root. Okay, and if we apply case 1 and then immediately after case 2, then for sure we can apply case 0 after that. Finally, case 3 bring everything in a situation in which we can apply case 4. So again, the only possible way to keep performing all this, to keep handling all these cases, let's see, as many times as it is possible, is to keep applying case 2. Otherwise, in a finite amount of time, we end up in solving the problem. Okay. So since by applying case 2, we basically push the problem towards the number of cases, number of times we can apply case 2 in the worst case scenario is the height of the regular tree itself, which is logarithmic, as we saw. So and this is enough. Of course, if we push the problem, since this is enough. Okay, So let's have a really quick look at the code. Removing removing a value from a replet tree is just as removing a value from the binary search tree. So you can basically reuse exactly the same function. And once you have removed something from the replet tree, a node from the replet tree, you need to check whether the color of the node you have removed was black or not. So if the color was red, for sure you haven't broken any rules, because you haven't changed the black height of any of the parent of the node you remove. You haven't changed you haven't for sure, by removing a red node, you haven't broke the rule that two red node in row can never occur. And so if the removed node was red, everything goes as expected. Otherwise, if the color of the node you remove was black, we need to fix it. Okay, and so how can we fix it? Well, we need to fix, of course, the new node which is placed on the former position of the node you removed, which is its right and left child. It depends on what you did to remove the node, of course. So once you establish which is the new node placed in the position in which was the node you removed, you have to apply fix remove replet tree. So what's fix remove replet tree? Well, fix remove replet tree is basically a procedure which keep checking whether you are in condition 0, condition in case 0, case 1, case 2, case 3, and perform all the operation we saw before. So just have a look at the code. It's not really difficult to understand from my point of view. So this is it, and that's all basically. Okay, so and that's all. So that's what I want to tell you about replet tree. So by using this procedure, we are able to insert this procedure. So the procedure we saw, we have seen until now from since the last lesson, we are now able to insert and remove element, preserving all the property of the replet tree, and then preserving the overall height of so the asymptotic height of the replet tree, which is logarithmic with respect to the internal nodes, so to the number of values stored in the replet tree itself. So again, a small recap. We are now able to solve the indexing problem. So we have discovered a data structure, a dynamic data structure, which is able to handle insertion, deletion, and searches, which is new with respect to the arrays, because as you may remember, the arrays wasn't meant to be enlarged or decreased in size. So this is totally new. Moreover, this data structure by default, automatically, let's say, is able to preserve the ability to search for a data inside itself in time logarithmic with respect to the number of data stored in the data structure itself at that moment, which again is equivalent basically to being able to perform a dichotomic search. Okay, and why this data structure how can we use this data structure? Well, simple example as seen at the beginning of this discussion on the motivation, and we saw that by using data structure we are able to to build up an index for a database. Of course, all the things we saw are based on the fact that the data we want to store on the Replit tree and the binary search tree is basically equivalent to the key of the Replit tree and the binary search tree, but it can, of course, it may be also different from this situation. So it may be the case that you want to index something which is not really, by using a key which is not totally related to the data you want to store. For instance, again, moving to the example we gave at the very beginning of this discussion, if you are dealing with database record, medical database, you may want to search for records of a patient by looking at its social security number, and the social security number is the key, so the value according which all the values are placed inside the data structure, while the recordings are not related to the ordering of the value. Okay, so in that case, of course, you may need to add some more members to your data structure, and we may call it payload, for instance. Okay, so the key is the value according which you ordered all the values you want to store in the data structure, and the payload is something simply related to what you want to store there. And this is quite useful, as already said, in building up an index. But you may use Replit tree to represent many different things. For instance, a quite interesting example is sets. So you may use Replit trees to represent sets. Why? Because sets usually are meant to store objects, insert objects, remove objects, and check whether an object is contained in them. So all this operation can be performed in a fast way and quite easily in Replit tree, and so Replit tree can also be used to represent sets, for instance. Okay, and this is all. This is basically all. So if you have any question about Replit trees, binary search trees, or any suggestion about how can they explain or anything, just please write me, send me an email, or write something below, write a comment below the video on YouTube. Okay. Oh, by the way, I missed to ask you at the beginning of the lesson to send me all your comments about the homework. I still missed them, so you need to send me something just to let me know what's going on, if you are okay, if they are too tough to be solved, if you need more time, or everything. Okay, don't be shy, please. I'm shy, I'm talking about all this stuff to you, so if I'm able to overcome my limitation, you should be able to. Okay, and that's basically all. So for the remaining part of this lesson, I would like to go through some exercises, if you agree. And this is basically because, as I said last time, your representative told me that you are in trouble with the homework, but she wasn't able to tell me why. So I decided to focus on recursive equation, which probably may be the newest things you saw until now about algorithm design. I mean, of course, all the algorithms are new for you, but they are not really tough to be understood, I think, at least I hope, but please send me a comment, otherwise I don't know what's going on. And so I think that probably since I'm my intention is to include some exercises about equation in your exam. I think it's a good idea to have some exercises about that. So if you agree, send me some comment on the chat, please. I will spend some time in trying to solve some equations. Please say something, otherwise I don't know whether you are still there. No one is speaking. Okay, let me move then to my whiteboard. Okay, this is my whiteboard. And let's try to solve some of the exercise we had. Let me go to the exercise, just to files. Please, really, I don't know what's going on, so it's really important for me to have your feedbacks. So send me an email, talk with your representative. I don't know. It's just really important for me. It's really important for me to know what's going on. So let me go to exercise. No, this is not exercises. This is it. Okay. So I'll try to solve exercise number 5 of homework on sorting 2. So homework sorting 2. Okay, exercise number 5. Let me copy. So first part of exercise number 5 is T1. Oh, let me write T1 n is equal to multiply T1 n divided by 2 plus big O of n. Okay, this is it. So the exercise asks to solve the problem both by using both recursion tree and substitution method. So let me do first of all by using recursion tree. So the first call. So here we are dealing with the time required to prepare or to conclude, let's say, the recursive call, which is big O of n. So let's choose a representative for it, for instance, C of n. So the first call, recursive call, costs in terms of non-recursive operation C n. Okay. Now we have two recursive call, and each recursive call takes time equivalent to the time required to solve the problem on a set which is half of the original set. So let me change the plan to say that here we are performing some recursive calls, in particular 2. This is due to this number, and since we are performing a recursive call, the number of value we are dealing with is just half of the original number. So here we need to, let me use another color, we need to deal with divided by 2 and divided by 2 and elements, and for each of that element we have theta of sorry, not theta but big O of n divided by 2 value to operation to be performed. So let me go back to the black, saying that the black is the number of operation required to perform this task. Okay, so this is there. Okay, so of course this goes on for a while, and at the ith level of my recursion tree I can find some calls which will deal with n divided by 2 to the power of I values. So this is the ith level of the recursion tree. So here again 2 to the power of ith. And of course for each call we need to perform big O of n operation. So we choose as a representative C multiply n, so this is C. Okay. Now how many of these call we have at the ith level? Well, at the level 0 we have one call, at level 2 we have level 0 one call, at level 1 we have 2 calls, at level ith we will have so let me write in this way. This will be 2 to the power of pi calls. Okay, so at the ith level we will have 2 to the power of I nodes in our recursion tree. Okay, so let me sum up everything. Of course we are lacking of the last level, which is let me go on the next slide. This will be the last level. The last level will be what's going on here. So this will be 1, this will be 1, and C and C. So if I try to see what's the height of the recursion tree, I can easily figure out it, because at each level I'm basically dividing by 2 the size of the number of the value I'm dealing with. So after log base 2 of n steps, I end up in dealing with exactly one element. So the 8 of the tree is logarithmic base 2 with respect to n, where n is the original number of value we were dealing at the beginning. Okay, so now let's try to evaluate per level the complexity of each call, but we are not doing it on all the three right now. We are doing it at each level. So let me consider exclusively the ith level, the generic ith level, because all the other levels will be the same. So here we will have 2 at the power of I calls, okay, and each call takes time c multiply n divided by 2 at the power of I. So let me write it. Which of course is basically c multiply n. Okay, so now we have all the data we are required to compute the overall cost of T1n. So T1n for sure will cost less than, and here I'm dealing with less than because I wrote less than because in our original equation we were dealing with big O of n. So all the cost mentioned here is not an exact cost, but is less than. Okay, so the cost at this level is less than, is equal or less than this value, of course. So, well, this is wrong here, but you know what I mean. So the sum up of all this is this one, but if you are wondering how much this level cost, of course you may say that the cost of this level would be less of this one. So the cost of T1 on n will be less than what? The sum of, and let me write everything again. So what? I moving from 0 up to logarithm base 2 of n of what? Of 2 at the power of I multiply c multiply and divided by 2 at the power of I, which of course is equal, and this is equal to c multiply n multiply the sum from I for I going from 0 up to logarithm base 2 of what? Of 1. And so let me write this way, and this is basically as writing c multiplied by n multiplied by, and here I can apply the Gauss sum and end up in logarithm base. Well, this is easy. No, it's not really necessary to apply Gauss sum. This is just logarithm base 2 of n. Okay, which of course belongs to big O of n log n. And this is it. Of course, I'm slowing down all the computation because I want to be to show all the steps. Now, this is for the recursion tree. So step phase 2, I don't know how to call it. Well, let me call it just prove recursion substitution method. So So the substitution method is just a method for, in which we are able to prove, we want to prove by induction that a given equation belongs to a given set of functions. So the idea is that I need, first of all, I need to guess the complexity of my equation, on my algorithm, and then once I've guessed the complexity, I can use some steps to prove it. So first of all, let me rewrite the equation. So the equation was t1 and equal to 2 multiply t1 and divided by 2 plus big O of n. This is it. Now let me say I guess that t1 belongs to t1n belongs to big O of n log n. This is a guess, of course, due to the experience. Okay, one question: what if we have changed the big theta instead of big O? Oh, I see. So let me go back. What if well, if I, so your question is what if this big O was a theta? Well, in that case, since we cannot assume anything about the base cases, so we may assume that the base cases are related to the size of the instance we are dealing with. Okay, and so in that case, the overall complexity should be computed as theta. Okay. So the question of your colleague was, what if here I was dealing with a let me change for a while theta of n. Well, in that case, of course, you may, to be fair, you should know what's going on with the base cases of the equation, because you may have base cases which are not related to the size of the equation, the size of the instance of the problem you are dealing with. Okay, so let's take the case of dichotomic search, for instance. Okay, so in the case of the dichotomic search, the base case, the best scenario you may have is the case in which the median element is the element you are searching for, and this case is not related to the size of the array. Okay, so if you have an array containing billions of numbers and the mean element of the array is exactly the element you are searching for, you end up in a constant time. Okay, but since we are dealing with an equation, you cannot guess this scenario. So there are no assumption on the algorithm. You can just have a look at the equation and assume, you can only assume that the base case are related to the number of elements you are dealing with. So in this case, so if this is the case, so if you are not able to guess any possible relation between base cases and the number, so if you are only able to guess a relation between base cases and the number of and the size of the instance you are dealing with, in this case, then all the computation you have performed right now bring you the conclusion that the complexity, well, here should be something like well, less or equal or greater or equal, and this is less or equal, greater or equal, and bring you the conclusion that this is theta of big N. Why I change greater or equal or less or equal? Because of course here you have to find a function which stand below and a function which stand above Cn, okay, sorry, Cn log n, and that's why I'm changing here. But we may have a look. Well, the next function should be an answer to your question. Okay, so the next in the next function we have a theta, but let me go on, otherwise we are missing the next function, which is much interesting than this one. So if I guess this condition, well, I can assume well, first of all, choose well, select better, select a representative for big O of n log n and big O of n. So let's say big O of n is for instance C n and C and log n and C prime, okay. Now okay, so assume that for all m smaller than n, T1 of m is smaller or equal, since we are dealing with big O, to C m log n. Okay, if this is the case, so let's try to figure out what's going on with T1n. Well, T1n by equation is equal to 2 T by the equation to multiply T1 of n divided by 2 plus, and here we have to place the representative of the big O equation, or let me write it here, n. But this is smaller or equal, since since n divided by 2 is smaller of n, we can apply our assumption and plan in C n divided by 2 multiply log n divided by 2 plus C prime n. Okay, and this is again this go out, so this is C n multiply log n minus C n log 2 minus plus C prime n. Now if this condition, so if this part of the equation is smaller or equal to 0, so if C prime n minus C n log n is smaller or equal to 0, and this case holds when let me see, when well, let me see what's going on here. Well, for so this grows more than this one for sure. So from a certain condition on, from a certain end on, this condition holds. And of course you may wonder for which condition, but I'm not able to compute it right now. Let me see. Oh yeah, if I move this one, so then C0n is greater than Cn log n, of course. So this can be deleted from this, and so n is greater or equal to 2 to the power of C prime divided C. Okay, so if n is greater than this, but of course you may revert all these cases and say that you want to select a C. So let me remove. You want to select a C which is so C must be greater than a C divided by log n, for instance, and then what's going on here? Well, this condition is greater than so the T1n is greater than C multiply n multiply logarithm of n. So we have proved by induction that for all n belonging to the natural number, T1n is smaller or equal to C multiply n multiply logarithm base 2 of n. By selecting an opportune C, of course. Okay, so this turned out to be the definition of big O. So we have discovered a C for which for all n this condition holds. So this is even stronger than big O. So it turns out T1 of n belongs to big O of n, and this is all. Okay, now let's move really quickly to point number 2. So point number 2 is so the equation number 2, T2, is this one, T2 equal to T2 applied to the ceilings of n divided by 2 plus again T2 of the floor of n divided by 2 plus theta of 1. Okay, now let me draw two trees. The first tree is a tree recording the number of value we are dealing with. The second tree is the tree of the costs, basically. So in the first tree we are dealing with let me use as we did before a different color. So the first call deals with n values at the beginning. So the first call takes care of n values. Then the second call, we have two recursive calls. The second call, the first of the second call, so this one takes care of the ceilings of n divided by 2. Well, the second one, so this one, takes care of the floor of n divided by 2 values. Okay. Now what's going on after a while? Well, what's going on just after another call? Well, from this call, of course, you will have again the ceilings of n divided by 2 ceilings again, and this is the first call, while the second call will be the bottom of n divided by 2. So the bottom, well, the ceilings of n divided by 2 bottom. Okay, so I don't want to write all the possible combination. Let me just write a few branches. This would be of course the ceilings of n divided by 2 and so on and so forth. So as you can see here, it's not really easy to figure out what's going on from an analytic point of view. So what's the floor of the ceilings of n divided by 2 I mean, it's not really easy to figure out what's going on here. However, if we have a look to the leftmost branch in the tree, we may figure out a possible maximum 8 for it. So when are we going to avoid to increase by 1 the floor of this value? So when this value is exactly the value of n divided by 2, well, of course this value will be equivalent to n divided by 2 exclusively when n is entirely divisible by 2, and this also holds for this condition. So when this value will be equivalent to n divided by 2 well, when n would be divided by 4, when n is divisible by 4, and so on so forward. So the best case scenario for all this computation is to have an n which is exactly a power of 2. So if n is exactly a power of 2, then all these steps are basically as dividing by 2, by 4, by and so on and so forth. Okay. So the point is, how tall is this branch? What's the length of this branch? Well, the length of this branch is the length that we may get having the next power of 2, so the power of 2 which is just next after n. Okay. So the idea is that if I was lucky, this n is the power of 2, of course, and this will be basically as divided by a power of 2n. But if this is not the case, the length of this branch is exactly as the length of the branch if n was the power of 2 just next to this n. Okay. So it couldn't be much more than, well, it couldn't be more than that. So how can we evaluate it? Well, for sure the next power of 2 next to n would be belong to n and n multiplied by 2. So let me write it. So for sure there exists a power of 2 between and to n. Okay, for sure. So the next power of 2, well, the next power of 2 with respect to n, so next to n, should be included between n and to n. You can prove it, well, however, it's almost straightforward. So the 8 of this branch, so the 8 of the branch in which you keep taking the ceiling, for sure is smaller or equal to what? To the logarithm base 2 of 2 multiply n. Okay. What about this branch? Well, this branch, so the length of this branch is analogous. While here we are searching for the next value, the next power of 2, so the power of 2 next to following n. Here we are searching for the power of 2 just before, the exact power of 2 just before n. Okay, so this would be greater or equal the logarithm base 2 of n divided by 2. Okay, so we have different length in branches. This would be at most logarithm base 2 of 2 multiply n, and this would be at most logarithm base 2 of n divided by 2. Okay, so let me go to the tree, and the cost of the tree would be c, because as you may remember, the equation was dealing with theta 1. So the non-recursive part of the equation was theta 1. So the first call cost c, we'll see as a constant. Then we will have two recursive equation, and their cost will be c again. Then we will have 4 recursive equation per first recursive call, and their cost will be c again, and so on so forward until, well, until what? Until the last level, the last complete level of the tree, which will be the level, at most level, logarithm base 2 of n divided by 2. Okay, and so if we perform all the sums, we end up in saying that our T2 n is at most greater or equal to I going from 0 up to logarithm base 2 of n divided by 2 of what? Of 1. Of, sorry, not c, not 1, but what? But c multiplied by what? Here we need to count the number of recursive call at the ith level, which will be of course 2 at the power of I. And if we perform all the computation, we end up in concluding that this would be c multiply all this stuff, which is 2 minus 1 to logarithm base 2 of n divided by 2 plus 1 minus 1. So this is 1 basically, and here this is c multiply 2 logarithm base 2 of n minus logarithm base 2 of 2 plus 1. So logarithm base 2 of 2 is 1. This is minus 1, this is plus 1, so this can be simplified. And this is to say that this is c and minus c. Okay, so the overall lower bound for our complexity is this one, which of course belongs to omega of n. This is the smaller amount of computation, the smaller amount of instruction you have to perform to solve the problem. And this is the result, and this is the complexity, the class complexity. Okay. Now, this is not enough to achieve all our proof. Why? Because here we have considered exclusively the part of the tree in which we have a complete. We have considered exclusively the complete part of the tree. So up to this level, we have all the recursive call, but we are missing the other part of the tree. So the part of the tree in which we only have the leftmost branches. Okay, and so let's try to figure out what's going there. So for sure, let's assume we have again a complete tree. So which is a over assumption. So in that case, we have if we assume to have a complete tree, we have that the complexity of our equation is for sure smaller or equal to what? To the sum for I going from 0 up to what? Up to the logarithm base 2 of 2 multiply n, which is the largest possible length of the leftmost branch of our tree, of c multiply what? C multiply the number of possible, the maximum number of possible elements on that branch. I mean, we can be much more accurate, but we don't care. You will see in a while why we don't care about to be more accurate. So here is c multiply the maximum number of calls at that level if the tree was complete, which are 2 at the power of I as before. So now let's try to simplify this equation, which all quite easily can be proved to be again 2 at the power of logarithm base 2 of 2 multiply n plus 1 minus 1. So probably before I was missing, no. Now, again, this is a multiplication, so we can reduce it to the sum to 2 logarithms, and so this is 2 at the power of logarithm base 2 of n plus logarithm base 2 of 2 is 1 plus 1 again, so this is plus 2 minus 1. Now, this is basically as writing c multiply, so this part 2 at the power of logarithm base 2 of n is n, while this is 4, so 4 minus c again. But again, this is linear, so this stuff here belongs to big O of n. So by doing this, we basically found a lower bound for our equation, an upper bound for our equation, and so since the lower bound, the upper bound of our equation are both linear in n, we can deduce that, so T2 of n belongs to what? Belongs to theta of n. Okay, and this is enough because we spent 10 minutes more than expected to perform this step. During the next lesson, which by the way will be on Tuesday of the next week, because we are going to face Easter break, so we will have an Easter break, and all the lessons on Monday and Tuesday are cancelled. So during the first part of the lesson we will deal with this equation, improving its complexity by using the substitution method. So during the first part of the lesson we will prove by using substitution method the complexity of this equation, and we will see something strange, and that's why I want to keep have a look at it. Okay, so if do you have different lengthening branches? Why we choose only one type of branch to find the omega limit? Okay, so let me answer this question, and then that will be all. So the branch. So let me say, in our tree we have. So first of all, our tree isn't complete. Okay, we have the longest branch is the branch on the left. The shortest branch is the branch on the right. Okay, this is clear. So by looking at the right branch, we can underestimate the total height of the tree. Okay, and so when we did this stuff, okay, we were computing an underestimation of the total cost of T2. And to do it, we basically sum up all the values on all the values, so all the cost for all the values on the shortest length. So for sure, up to the shortest length or up to the shortest branch, the tree is complete. Okay, so trying to compute the omega, we are underestimating the cost of the T2, and this is done by summing up all the costs for all the calls that we are guaranteed to be required, and that's why we sum up all the costs up to this level, because this is the length of the shortest branch of our tree. Okay, so up to this level we are guaranteed to have a complete tree. Okay. Yes, the tree isn't complete. So one of your colleagues is asking whether the tree is not complete because of the floor the ceiling operation. Yes, it is not complete because of that. But by observing that, by observing this property, so there is a power of 2 between n and multiplied by n, and of course there is a power of n between n and n divided by 2, we can compute the length of these two branches. Now I have to go, so thank you for the attention, and see you on Tuesday then, and happy Easter, and that's all. I hope you enjoyed the lesson, and so again, happy Easter, and let me know what's going on with the homework. Okay, see you.